light since we left. Much quicker than
All right, we'll go ahead and get started. Hello to all of our colleagues on Zoom. For those of you who don't know me, I am Laura Klepper. I'm the Associate Director for Education here at the Center for Acoustics Research and Education at the University of New Hampshire. And welcome to the second seminar in our fall seminar series lineup, where we are highlighting some of the early career researchers that CARE has recently welcomed aboard onto the team. So today, it is my extreme pleasure to introduce Dr. Thomas E. Blanford received the BS degree in electrical engineering from the University of Notre Dame from Indiana in 2012, and then received a PhD in acoustics from the Pennsylvania State University, State College, Pennsylvania in 2019. From 2012 to 2017, he was an engineer with Analog Devices and InvenSense. Am I saying that right, Tom? InvenSense, where he developed low power, high performance micro electromechanical system, otherwise known as MEMS microphones. From 2019 to 2023, he was an assistant research professor with the Applied Research Laboratory at Penn State with a faculty appointment in the graduate program in acoustics. And we are very happy that he is now a research assistant professor with the Center for Acoustics Research and Education and the Center for Coastal and Ocean Mapping here at the University of New Hampshire in Durham. His research interests include the designing and modeling of sonar systems, acoustic navigation, and signal processing in acoustics. So with that, I am going to introduce Tom, who's going to be presenting developing low-cost instrumentation for underwater acoustics research. We'll pass the mic here.
Thank you. All right. So a lot of my work is in developing acoustic sensors and instrumentation, and that involves kind of a multidisciplinary set of tools. So it involves some transduction, converting electrical energy into acoustic energy and vice versa. A bunch of electronics, some systems engineering, as well as some signal processing. And I got into that early in my career when I was with Analog Devices. So as Laura said, at the time, they were interested in making MEMS microphones. And so all that means is we were making a high performance microphone, machined out of silicon, using the same processes you'd use to make a computer chip, but we were trying to make a moving structure. So in a small package that's a few millimeters by a few millimeters, we were putting that micro machined silicon diaphragm and coupling it to an integrated circuit that had a preamplifier and an analog to digital converter. And these show up now in everything from your iPhone to hearing aids. Most recently, I was at Penn State, where I was focused on underwater sound, doing transduction for sonar systems, so underwater projectors and hydrophones, mostly for imaging sonar systems. Since June, I've been here at UNH. So if you're interested in talking about research or non-research, please come find me. If you're on campus over in Chase, I'd love to chat. What I want to talk about today is developing low-cost instrumentation for when we're working in acoustics underwater. And a lot of times when we approach a science question that involves some acoustic elements, we say, let's just get a really good sensor. It's obviously going to collect all the data we're ever going to need. We can figure out whatever we need to do with it from there. We might get a quote, have a bunch of sticker shock, and then to get it low cost, we think about how do we get rid of some functionality that maybe we don't need. And I think that's a little bit of a race to the bottom. So I want to talk about a different approach that requires first taking a step back to look at what are the problems we're really trying to solve, and what's the data that it takes to get us there. And there is a path through all that that lets you develop custom instrumentation that's highly effective, but still low cost, and is still adaptable to more than one type of problem. I'm going to talk about this in the context of two projects. The first is a compact correlation velocity log, which is a type of acoustic navigation aid. The second is AirSAS, which is an acoustic imaging experiment. We're going to start off with the navigation aid. So the compact correlation velocity log arose out of the need for a navigation instrument for a small man-portable sized underwater vehicle. When you navigate underwater, you don't have access to GPS, so you need alternate methods. And typically what's done is you use an inertial navigation system, an accelerometer, and a gyroscope. But those drift over time, and you need some sort of acoustic sensor to correct for that drift. And that gives you an estimate of your position or your velocity relative to the seafloor, and the seafloor is not moving. On these small little vehicles, there's a number of challenges. One, they're small, so you don't have a whole lot of space to put your acoustic array. Because they're so small, they have limited battery capacity. So anything you put on there has to be low power. And finally, these sorts of vehicles are somewhat expendable. And so if it's not going to come back, you don't want to put a really expensive sensor on there. Generally, acoustic navigation is done with what's called a Doppler velocity log, or a DVL. These are pretty widely commercially available, and they work by transmitting several narrow beams of sound at grazing angles to the seafloor. And you estimate your velocity based on the Doppler shift from each beam. For anyone who's used an acoustic Doppler current profiler, an ADCP, this is the same sort of technology, but instead of pointing your beams up into the water to sense currents, here we're pointing them down to the seafloor. For these to be accurate, these beams have to be extremely narrow, on the order of just 1 to 2 degrees wide. So when you don't have a whole lot of space for your array, your transducers can only be so big. To get these narrow beams, it forces you to operate at very high frequencies. And on a platform like this, it would be in the megahertz. High frequencies underwater are attenuated the most. So you need a whole lot of power to get measurable returns off the bottom if your vehicle's at any significant height off the seafloor. And on these tiny little vehicles, they just don't have the battery capacity to do that. And so it's not going to work. An alternative approach, much less common, is a correlation velocity log. These work by transmitting a single broad beam at normal incidence to the seafloor. They use the spatial coherence of seafloor scattering. So spatial coherence is just how similar is the field as I measure it at different points in space. And they estimate the velocity by correlating the signals across an array of hydrophones. A single broad beam means lower frequency than a comparably sized DVL. Lower frequency is lower power. It's only 1 beam transmitting, it's opposed to 4 in most DVLs. So that's 4 times less power you have to put into the water. And finally, near normal incidence, that's where the scattering strength of most marine sediments is greatest. So you don't have to transmit a whole lot of power to get a really strong backscattered signal off the bottom. So all of this is favorable geometry for low power operation. What we have to figure out is how to make it fit on these tiny little vehicles. A CVL works based on what we call the principle of waveform invariance, which is kind of a silly name. All it says is that 2 signals are going to be highly coherent or highly correlated if they share a common midpoint between their transmitter and their receiver. So here I'm illustrating a really simple CVL array with a projector and 2 hydrophones. The midpoints between the two we call the phase centers, and I've drawn those as those unshaded boxes. And at some time later, our arrays move forward to where it's now shown in green. At this point in time, we have overlapping phase centers between the projector and the first hydrophone at the time in blue, and the same projector, but now the second hydrophone at the time in green. With this, I've just removed all of the elements except those that correspond to the overlapping phase centers. And you can see all we're doing is maintaining this common midpoint with our signals. We'd find the amount the array had to move forward to get to this condition is half the separation between the 2 receivers. And if we call the time it took to get there tau, we have an equation for our velocity. From that equation, you can kind of motivate 2 ways to think about operating your CVL. One of the earliest approaches people took was a temporal CVL. Here we're going to hold D, the receiver separation constant, and we're going to search for tau, the time that it takes to get to maximum correlation. This lends itself to some really simple arrays with just a projector and 2 hydrophones, but they turn out to be not that accurate. You have to use narrowband waveforms, so you don't have a lot of unique and independent information coming in to work with. And they're a 1-dimensional velocity sensor. And so if the vector separation between your 2 hydrophones isn't perfectly aligned with the actual velocity of your vehicle, you're going to get the wrong answer. So in practice, what's done is a spatial CVL. Here we're going to hold tau constant by transmitting 2 pulses into the water at known temporal spacing. And we're going to search for D, the receiver separation that maximizes correlation. This is a nice approach because it gives us 2D or 3D velocity estimates, so X, Y, and Z components. But they tend to need some pretty complicated signal processing, as well as large and densely packed receiver arrays. Now, a large, densely packed receiver array doesn't really scream low cost and small to fit on a underwater vehicle. So the first thing we need to do is understand what goes into designing this array to help us find these receiver spacings that are going to maximize correlation. And there's a whole lot of factors that go into it. So we're going to consider for a moment another really simple array geometry, this time a projector and 4 hydrophones. The phase centers are the circles in the middle. And between our 2 pings, the array moved forward about 1.5 phase center spacings. And so we're just going to look at phase centers now and ignore the actual projectors and the hydrophones. If we make a plot, where on the x-axis are all the possible separations between the phase centers in our array, all our data points are going to be at integer multiples of delta, because that's how our array is spaced. On the y-axis, we're going to plot the correlation between the signals we measured on ping 1 and on ping 2. When we do this, we get a few points that are reasonably highly correlated, and they're at 1 delta and 2 delta. Our array actually moved 1.5 delta, and these are just the nearest points where we have data. If we wanted to estimate velocity from this, we could fit a curve through this data, and the peak of that curve is going to pretty closely correspond to the actual advance of the platform. Now we're trying to do this with signals that scattered off the seafloor, and backscatter from the seafloor, especially at high frequencies, tends to be random in nature. A consequence of working with random-like data is that it's really only the highly correlated points that are going to be any value to us in doing this fit. Because the points of low correlation have a lot of statistical estimation error. They have a lot of variance, so they vary around their normal value pretty wildly. They also have a lot of bias. And so if we try to average that down, they're going to average out to a value that we're not expecting. So we need more points in the top part of this plot, the green regime. One way to get that is to add more hydrophones to our array. Densely packing this array with the points now in blue gives us more data points in the green regime. We have a bunch of high quality data we can use for our curve fitting. But if our vehicle is moving a little faster, or instead of moving 1.5 delta between pings, it moved even more than that. Well, now our receive array has to grow because we don't have enough phase centers to get overlap between the 2 pings. And so you see how this is going to push towards large arrays with a whole lot of elements. The final thing we can use to get more points in the green is to transmit with more bandwidth. Using more bandwidth increases the amount of independent information coming back in our acoustic signals. More information means less statistical estimation error, more high quality data to work with. We can see the challenges we're up against in making this small and low cost. The first is we have to get the channel count down, right? Each additional channels, another transducer, another preamplifier, more signals, which require more processing power. So something has to happen there. We also need to break this relationship between the physical array size and the accuracy of our velocity estimates. And finally, we need to put as much bandwidth into the water as we're able to, because more bandwidth means more high quality data to work with. The first problem here we sought to tackle is making the array sparse. So we only want to put in the hydrophones into our receive array that we need to get the best quality velocity estimates, and no more hydrophones than that, because each one's just going to add costs that we don't need. So we developed a model to understand the relationship between all the receivers in the array. One thing we found is that if you have a uniformly spaced receive array, so the separation between all the elements is the same, well, then if you're trying to estimate the correlation at a specific spatial offset, you're going to make more than one estimate of that. So in this example, if we were interested in the coherence of receivers separated by a distance delta, we have 2 ways to do that. Because the pair of hydrophones, or it's the same with phase centers really, 1 and 2 have the same spatial relationship as pair 3 and 4. And so if the pair in blue isn't telling us anything that the pair in orange already told us, we don't need the pair in blue. On the other hand, if it's giving us more information, that's all going to help us get a better velocity estimate. And so maybe we do want to keep it. We need to know what that relationship is in order to design our array. So we developed this model and validated against field data to know it's going to work. And what it tells us is somewhat intuitive. Is these 2 redundant pairs of receivers with the same separation get really close together in your array, then they're telling you the same thing and they become dependent on one another. As they get really far apart, they start to give you more unique information. The particulars of the relationship depend on some array design as well as some geoacoustic properties, but we have a model and we can use that to optimize for our array geometry. The next thing we sought to do was tackle this problem of our velocity estimation accuracy being dependent on the size of our array. To break that relationship, we had to rethink the way a CVL is going to operate. And what we came up with is we call a spatial temporal operating paradigm. And this blends both the spatial and the temporal techniques for a CVL I mentioned earlier. What we're going to do is transmit multiple pulses into the water. Here I'm illustrating just 4. In practice, it's many tens or hundreds. We're going to look at a 2-dimensional receive array now. And so think about hydrophones spaced around a circle. So our phase centers now are 6 elements spaced around a circle, shown there in black. And as we receive the echoes from each ping scattered off the bottom, our array moves along with the vehicle. And by the time we've received all of these echoes, we've formed a synthetic phase center array, which I realize is kind of an abstraction on an abstraction. But this synthetic phase center array has both larger spatial extent and finer spatial sampling density than our physical array on just any pair of pings. So using this ensemble of pings gives us much higher quality data to fit a curve to. And that's what we have to do to estimate velocity, because it's unlikely that we have 2 phase centers that perfectly overlap. So we have to do some interpolation to figure where that peak in the function is going to be. But the spacing of all our data points here, we don't know, because it depends on the velocity of the vehicle moving along. And that's ultimately what we're trying to find. So we have to do a pretty complex fit to the data. And as we give it as input parameters, the physical array geometry, that's x naught in the equation, and all the spacings in time between the pulses that we transmitted. One of the things that comes out from this fit then is v, our 2-dimensional or 3-dimensional velocity vector of the platform. With this concept, we then sought to demonstrate it with a prototype. So we built up this physical array. It's got a projector made out of a piezo ceramic disc, and that projector is coupled into the water through a matching layer. And the matching layer helps us get the most bandwidth into the water possible. Our receive array, the hydrophones, are also built out of smaller piezo ceramic discs. And the whole thing's built on a layer of syntactic acoustic damping material. That's the Satum backer there. That's a material that's highly attenuating. And so it's going to attenuate signals being transmitted out the back of the array or received from the back of the array. So we're only sensitive to sounds going between the array and the seafloor and not the array and the sea surface. You can see how small it is. So we achieved our objective there. It's about 1.5 inches by 3.5 inches. And I've shown a US quarter there to try to illustrate the relative size. So to recap, to make this thing small and low cost, we had to do a few things. First, we had to develop a model to make the array sparse. That shows up in the hydrophone array design. We then had to rethink the operation. So that shows up in the signal processing. We did one more thing to make this thing low cost, is we removed the quarter before finalizing the assembly. So that saved us an additional 25 cents. All right, we took the array, sans the quarter, put it on the bottom of a pontoon boat and tested it at Seneca Lake in New York. We tested over a variety of operating conditions, varying the depth and the speed of the platform. We had a high quality reference velocity. So in these plots, that's the curve in black. The reference came from a fiber optic inertial system aided with GPS and real-time kinematic corrections. So we had about as high accuracy reference velocity to compare to as you can buy. And in our receive array, we have 16 elements. You actually don't need all of those for this to operate. We put 16 elements in there so we could evaluate some of the trade-offs in the array geometry. And I'm going to talk about 2 of them here. The first is the subarray in blue. So it's a little bit of a larger aperture. And the second one's the subarray in red. And they share some common elements, but the array in red has a bit of a smaller aperture. The velocity estimates are separated into forward and athwartship components. So forward in the direction the vehicle's moving, athwartship side to side. It's a pontoon boat, so almost all the velocities in the forward direction. But you can see it does a reasonably good job with tracking with the reference velocity. As the boat ramps up in speed, we follow that. As it moves side to side, we follow that as well. One error we believe exists in this data is we believe the array was slightly misaligned with the forward direction of our inertial navigation system just by a few degrees. If you correct for that offset, the two curves would line up a little bit better. But there's also some discrepancies that doesn't explain. And those are going to come from this relationship between the physical size of the array and the amount of independent information we got in. That model we had to use to make the array sparse. The red array performs a little bit worse because the hydrophones are so closely spaced together. We're not getting as much unique statistical information off our signals from the seafloor as we are in blue. And so the blue does a little bit better estimating velocity. All right, now we're going to change gears. We're going to talk about some imaging sonar. So AirSAS is an in-air synthetic aperture sonar experiment. Synthetic aperture sonar is just a way to form high-resolution images using sound. Typically, it's done underwater with an array put on an underwater vehicle. So in this example, the synthetic aperture sonar is the white section of the vehicle. An inexpensive synthetic aperture sonar is generally a few $100,000. And that's just for the sensor. You still need an underwater vehicle. You need to go out to sea. You need a crew to do all of that work. So it's a really impressive sensor. It's a really interesting area of research, extremely expensive. The way a synthetic aperture sonar works is trying to synthesize a very large array. If you want a high resolution array, it needs to be very large with a lot of elements. And it's just plain impractical to make an array that's hundreds of meters long with billions of elements. So instead, you can make a small physical array, move it through the water, pinging as you go, save up all of that data, and synthesize a much larger aperture, so synthetic aperture. This vehicle formed the example image there, where it imaged a downed submarine. To make that image, it flew first along the length of the submarine, and kind of when it reached the end, turned in about a 90-degree angle and flew along the bow. That is a cool thing with synthetic apertures. With a physical aperture, once you build your array, you're stuck with that geometry. With a synthetic aperture, it can be any shape you can drive in. The pixel resolution in that image is on the order of a few centimeters. So it's extremely high resolution for an underwater imaging sensor. You might be trying to drive in a straight line, but underwater dynamics end up giving you some pretty challenging data to work with. So in our synthetic aperture sonar, our array, the orange section, typically has a projector, that's the large orange block, and an array of hydrophones, the smaller orange blocks. The projector pings, the sound scatters off of the seafloor and any objects that are down there. And then the array moves along with the vehicle, pinging as it goes. We were hoping for a straight line, and we sort of got it, but really what we have is kind of an irregularly spaced, uneven line array. And we have to compensate for all of that unwanted motion before we're going to get an in-focused image. And that's part of an active area of research in synthetic aperture sonar, improving image reconstruction. We're also interested in using machine learning to look at these data products, detect things that we're interested in, and tell us what they are. The two images here, I think, are pretty good examples of what we're after. So the image on top came off of an underwater synthetic aperture sonar. We believe it's an image of a man-made cylinder, but it's pretty out of focus. You can see that there's an object there, but it's hard to tell what's going on. So we developed a improved motion estimate for the platform, and we got the more in-focused image on the bottom. There's still things there that we don't understand. Right behind the cylinder, we see these vertical streaks. Our hypothesis is that's sound interacting with the cylinder in a pretty complex way. When sound first impinges on a cylinder, it backscatters, and that gives you an estimate of the shape of the cylinder. But some of the sound is also going to couple on, and it's going to propagate around the circumference of the cylinder, radiating back to you with each pass. And we believe that's causing these periodic streaks in the data. Now, that tells you a whole lot about the cylinder, because it tells you its geometry, but it also tells you something about its material properties. And that's the type of information we're seeking to leverage with these sensors to make decisions on. Developing those algorithms, though, requires some really high quality data because you need almost perfect ground truth to know exactly what was down there, what it's made of, and where it was. You also need to start building up a data set to do this on any sort of ensemble. And so getting that from a fielded sensor is pretty challenging. With the expense of SAS, it's also hard for new researchers and students to get involved just because no one's got $1 million laying around. But sound travels in air too, and we started wondering, do we have to do this work underwater? You can generate high quality data in air with consumer audio equipment, just loudspeakers and microphones. You can integrate it in facilities that don't require tanks or really any underwater specialization. And what we found is, yes, you can use this to help solve problems underwater. And what we came up with is air SAS. So this is our in-air synthetic aperture sonar. It consists of a loudspeaker that transmits signals and 2 laboratory microphones to receive them, or more microphones, as we'll see. In this case, we've housed it in a small anechoic chamber. Targets are put on a turntable, so they rotate relative to our array, and the array is also on a linear actuator to move up and down relative to the targets. So this lets us form our relative motion between the array and the targets. We use audio amplifiers to transmit signals and some basic signal acquisition equipment to digitize them. And we form these really rich data products. So this is on the right, a synthetic aperture sonar image of that hollow copper pipe we put on the turntable. You see the outline of it, but you also see all of this energy extending out in space. And just like that cylinder we thought we encountered underwater, where sound was interacting, propagating around the circumference and re-radiating, a similar thing's happening here. If you flicked that cylinder, it would ring like a bell. And the same thing's happening as sound impinges upon it. It backscatters, that shows you the shape, and then it rings down because structural modes got excited. A lot of synthetic aperture sonars done in a linear collection underwater because that lets you survey the largest area. But the simplicity of working in air just lets us move our same loudspeaker and microphones to a different motion platform. Here we put it on a 5-meter linear actuator. And in front of it, we built a sandbox and filled the sandbox with plastic beads. The plastic beads kind of simulate a rough interface like an underwater seafloor. And then we put solid polyurethane spheres, those black spheres, on top to act as some targets to look at. The array moved down the track, paying as it went. We saved up all of the data and reconstructed this image, which has a lot of the features we're interested in studying. There's a speckle background formed by the rough interface of those plastic beads. The targets provide highlights because they stick up a little bit above that seafloor, or fake seafloor rather, but they also cast shadows onto it. That shadow is an important feature underwater because it tells you something about the height of the object. So with some really simple equipment, we're generating highly controlled data to start to develop algorithms. So what are some of the things we've done with it? One of the first things we studied was this late time energy. So when sound encounters an object, is re-radiated later in time, like we saw with the cylinder. And we studied this with a soda bottle, looking at it with the cap on and with the cap off. The cap off is on the right, and you see the outline of the bottle, but comparing the two images, you also see these streaks of energy. And our hypothesis was, well, that's not there when the cap's on the bottle. So this must be energy that entered the bottle and was re-radiated later in time. And we wanted to see if we could focus that. If it focuses, it should focus at where it was re-emitted from the bottle, and that would be at the mouth. So our hypothesis was, if we progressively focus this image in time, we will eventually see that image focus at the mouth of the bottle. We developed an algorithm to do that and tested it on this data. And here we're marching through in time, progressively focusing the image, and we're seeing all that energy come into focus exactly at the mouth of the bottle. Because we had highly controlled data, we knew we got it right. We also wanted to explore 3D reconstruction. So for this work, it was in collaboration with some colleagues at Arizona State and Dartmouth College. and we were leveraging some techniques in the computer vision world. We 3D printed these two objects. The top is the Stanford armadillo, and this is the Stanford bun. They're actually pretty common objects in computer vision because the whole community knows what they should look like when you've reconstructed them properly. But they're also pretty complicated, right? They're not just like simple cubes or spheres. So we took these objects, we used our circular geometry here, put them on the turntable, and so they were rotated relative to our array. But then to get 3D reconstruction, we also needed vertical aperture, and so our array was moved up and down on the vertical linear actuator. First, we reconstructed the data with traditional delay and sum beamforming. This is what's done in most underwater synthetic aperture sonar, and it does an okay job, right? You know, you can see blobs sort of where the targets are. You can make out the ears of the bunny and the arms of the armadillo, but it's not great. We then looked to computer vision and some machine learning techniques to see if we could do better. And the reconstruction algorithm came up, we're calling neural back projection. And we developed a machine learning network where we gave it as inputs all of the places we pinged the objects from, the waveform we transmitted, and then all of the measured acoustic signals. And we asked that network, given all of this information, what must have been down there to generate these signals that we measured? And the array worked through the data, and it came up with these much higher quality reconstructions of the two objects. Because we started in air, we were able to iterate on this experiment, studying sensitivities to different collection patterns, different transmit waveforms, and understand what's going to make this algorithm work and not work. And once we got it working in air, we moved to underwater data and got it working there too. A final thing we've done, because we have really tight experimental control, is we can study some really sensitive effects. So we're back with our linear actuator in our sandbox. And here we've just got our bed of beads. And we formed an image of it. And the image on the top. And it's just a rough interface. So the background it forms is a speckle field. Between collecting it once and collecting it again, I took a broom and just ever so gently brushed the top of the surface of the beads in a few places. You couldn't even see with your eye that we had done anything to it. Now, a synthetic aperture sonar image is actually complex valued. It has a magnitude and a phase. The magnitude is just a representation of the scattering strength. So brushing the beads isn't going to change the scattering strength because we didn't really change its composition or its roughness too much. But it is going to change the phase because phase is extremely sensitive to position. And brushing around a few little plastic beads change the position. And so when we form a second image, the magnitude is what I'm showing here. And it looks the same because the scattering strength is the same. But if we go pixel by pixel, comparing the two images and asking what's different, we can find the pattern that I brushed into it, which is UNH. And I think this is a pretty cool result. With some really simple equipment, a loudspeaker and a few microphones, we're looking at these really sensitive effects. And studying small-scale changes underwater with a high-resolution sensor, like a synthetic aperture sonar, is absolutely a problem of interest to the underwater acoustics community. We do need to be honest, though. We're still studying an analogy. We're not yet working underwater. And so working in air isn't exactly the same. The way sound interacts with structures, objects still ring in air as they do underwater, but the frequencies and the angles at which the sound couples on and off are going to be different. Furthermore, a bed of plastic beads has similar properties to a rough seafloor, but it isn't a real marine sediment. And so when we're working in air with these analogies, we need to make sure we're still being sufficiently general, because if we're too in tune to the specifics of acoustics in air, when we go to move underwater, where the ocean dynamics, the noise sources, and the propagation mechanisms are different, things might not work the way we expected. But studying analogy lets us test these really risky ideas before we bear the expense of going out to them. Okay, we'll wrap up here with a few points. So I want to come back to how important custom instrumentation can be for a study. It really lets you get exactly the data you want. Developing that sensor, though, is often a research project in and of itself. It is possible in the end to get something that's inexpensive, effective, but adaptable to more than one project, but it's going to take some work. to think about the research objectives, the qualities of the data you need, and you really have to go tackle the obstacles that are going to be in your path to get there. But once you do, you can find some pretty unconventional approaches that let you do some pretty cool science. And I'll stop there, and if we have time, take a few questions.
Well, thank you so much, Todd. Yell into the microphone. People who are on Zoom, if you have a question, you can just put it in the chat. But we'll start with the room.
This is a great presentation. Thank you. The first half, when you're talking about the phase.
Yeah, the phase centers.
You would do that on pressure, right?
Correct.
Things I was thinking as you were watching it, don't fish, like with their lateral line that are sensing particle motion, do they do the same thing as they swim through the water?
That's a really good question. I don't know the answer to that, and I'm not sure we know a good amount about the coherence of pressure fields, and I don't know that we know as much about the coherence of particle velocity fields.
Huh.
But
I was just thinking that's what my mind went to as a biologist, as you were describing your technology. I feel like that sounds very similar to the lateral line.
I've often found the natural world to be pretty humbling, that just because we thought of it doesn't mean fish haven't been doing it forever.
No, I know.
Yeah.
Building off of that from the animal world. So you mentioned that bandwidth for the phase.
Yep.
Bandwidth affects it. But does the overall signal design too? Like I'm thinking like bats with their FM downspeed calls. How much does signal design impact?
So for these particular signals, not a whole lot, because when the sound interacts with the seafloor, which is what we're really asking it to do, all that phase information is getting randomized anyway. And so if you were trying to do something maybe a little bit more clever of transmit a coded waveform to keep your transmit levels really, really low, that might help you. But in terms of just navigation accuracy, I don't believe it does. Yeah. Yeah. It's a good question. Yeah, so Jenna's wondering in our experimental results here, especially on the top plot, there's a few peaks in the data. It looks, around measurement number 125 and maybe 450. And she's wondering what they are. We don't know. Our suspicion is it's something in the water column that basically prevented our sound from getting all the way down to the seafloor. The fact that we didn't see it in the ground truth means it's not, some really unexpected vehicle dynamics like going over a wave. But no, that's a good question. There's unexplained phenomena in the data. I know. Correct. Yep. We did apply for a patent on it. The hurdles to technology adoption are many. So doing the research here is the first one, but with the patent and actually with adoption, the business case is often the harder one. And things we're finding is the underwater vehicle community isn't ready for it. That they have more hurdles they want to solve before they need a better navigation aid.
I thought of another question.
Yeah.
So sometimes bats do something called strobe grouping.
I'm not.
It's when they'll produce like a couple pulses in rapid succession, followed by longer pulse, and sometimes they'll be starting to receive echoes where the next pulse has been put back, it's been thought that is needed in navigation.
Okay.
Have you done anything with playing around with something like that, like the temporal nature of how much those signals are put out?
We haven't. That I looked at it a little bit in simulation, and the biggest thing it does is it makes your fit at the end even more complicated, because rather than having a single variable of how much you move between pings. It now depends on the actual spacing you put into the water. But that's an interesting idea.
There is a, I guess it's technically a question veiled as a comment from Dr. Anthony Lyons. Does one need a Tom Blanford to achieve low-cost sensors in general? Question mark. I'm happy that we have a Tom Blanford language.
Well, I'm flattered, Tony. I really don't think you do. That you know, it does require some knowledge of transduction and some knowledge of electronics, but I think these are also things that can be developed by teams. That I obviously didn't create these results alone, and I had a lot of help. And I think a team of researchers can all come together, take a similar approach, and get a similar result.
Other questions? Can you ask me the right?
Any other questions online? I think Jen has one in the meantime.
You say they're inexpensive.
Yeah.
How much total?
Yeah. So it's expensive is all relative.
Yeah.
The correlation velocity log, we did some estimates that if you ultimately got it into like a manufacturing flow, could be a few $1,000s. The AirSAS, we actually found that that's an interesting experiment looking at some trade-offs, that you can do it for tens of dollars. To study some of these more subtle effects, it helps to spend a few $1,000s.
No, there's no more online. So you're good. Okay. Is there any demand for something like an AirSAS?
We believe yes. A few other universities actually have taken our results and they're standing up their own. For doing their own research. So rather than having the one AirSAS in the country collect their data, they can use it to train grad students. It's a pretty intuitive sensor. You know, you hear it ping, you hear a sound come back, and they can collect their own data and investigate their own questions.
Demand for a teaching element.
There's a demand for a teaching element.
But is there a research or applied demand? I'm just trying to think what.
So, I mean, we're tackling a lot of questions in the machine learning world using AirSAS for ONR right now. I have some colleagues at Georgia Tech who are interested in using it for acoustic communications as well. That's not an area I know much about, but I know they want to.
I mean, imagine if you could acoustically scan an object and then recreate it and then transmit it on a computer. It's like acoustic teleportation. Down the line. Virtually. Yeah. I don't think we have any more. Oh wait. Oh yeah. Anthony has a comment that, or Tony has a comment. AirSAS can be used for AI type work.
Yeah.
Yeah. Well, thank you so much, Tom.
Thank you.